So now we're going to look into something very interesting as far as chemistry is concerned. And this has to do with what is called radioactivity. All right. Natural radioactivity is the focus of this particular chapter. So the first thing we're going to talk about is what we call radioactive isotopes. Now, isotopes, if you remember, are different atoms of the same element, but they have different mass numbers. All right. And what you'll find is that there are some elements that can have some isotopes that are unstable. And what that means basically is that such an isotope will emit radiation, and we're going to talk about the different forms of radiation to form something more stable. All right. And there are some examples of radioisotopes that are given down here. So let's look at the case of magnesium. Now, in the case of magnesium, for example, we have one stable isotope, which is magnesium 24. So the mass number for this form of magnesium is 24. However, you have two unstable radioisotopes of magnesium. One is magnesium 23 and the other one is magnesium 27. So the stable one will just basically not undergo any reaction, any nuclear reaction to form anything more stable because it's already stable. While the radioactive ones, which are not stable, will basically emit some form of radiation to form something else, which would be more stable. We have some other example here. Iodine, you have a stable form of iodine right here, iodine 127, but you have some unstable radioactive forms of iodine, such as iodine 125 and iodine 131. All right. There are some elements that have no stable isotopes whatsoever. Uranium is such an example. There are no stable isotopes of uranium. All forms of uranium are unstable, such as these two right here, uranium 235 and uranium 238. All right, so these are all examples of radioactive isotopes as well as stable isotopes. Okay, so as I said before, radioactive isotopes basically will form a more stable atom by emitting some form of radiation, right? And the type of radiation that is emitted can take on different forms. And here is a list of the different types of radiation. You have alpha particles, which is basically the helium nucleus, as you can see by this symbolism here, where the mass number is 4 and the atomic number is 2. So this is the helium 4 nucleus. You have what is called a beta particle, which is basically an electron, where the mass number is 0, but the atomic number is said to be -1. You have a positron, which is basically the opposite of an electron, where it has an atomic number of +1. Gamma rays is basically some form of radio waves or radiation which has basically no mass or no mass number, no atomic number. And then you have the proton. The proton is basically the hydrogen nucleus, hydrogen 1 nucleus, where the mass number is 1. And then you have the neutron, which is neutral, so therefore it has an atomic number of 0, designated, I'm sorry, and the mass number is 1. So these are the different forms of radiation that can be emitted by some unstable isotope. Now, let's look at in more detail a couple of the particles that we just discussed. The alpha particle, as we said before, is a helium-4 nucleus. It is made up of 2 protons and 2 neutrons. All right, so therefore that's why the mass number is 4. The mass number is the sum of the number of protons and neutrons. Now, the beta particle is basically a high-energy electron, as we said before, and we designate the atomic number as being -1 and the mass number being 0. The positron is also called the positive electron. It's basically the opposite of an electron because the normal electron is negatively charged. So the positron is basically positively charged, so therefore the atomic number is +1. And as far as gamma rays are concerned, it's a form of high energy radiation that is released from a nucleus in some instances. So that's basically a summary of the different types of particles that we'll be working with. Now, the thing about one important aspect of studying radioactive nuclei is that they are very dangerous to work with in a lot of cases. All right, and therefore, people working in the nuclear industry, they tend to have to basically take some precautions, which includes, protective gear, clothing, gloves, goggles, etc. And that's because the radiation, depending on its intensity and so on, can actually penetrate certain materials like paper and clothing, depending on the material. You know, so you have to basically, take special precautions. So as stated here, the radiation protection requires some paper and clothing for alpha particles, right? If you're working with radiation which produces alpha particles, a lab coat or gloves for beta particles, and in the case of gamma rays, you're going to need a lead shield or a thick concrete wall for gamma rays, all right? You have to also limit the amount of time spent near the radioactive source and also try to increase the distance from the source. So these are precautions that are normally taken by people working in these industries, the nuclear industry. So this here is a table which basically summarizes the different forms of radiation and their penetrative power, all right, in terms of the distance that they travel in air and in also the penetrative power in terms of tissue depth. We're talking like biological tissues and so on, and the type of shielding that is required for them. So just to highlight a couple of examples, in the case of alpha particles, it will travel a distance of about 2 to 4 centimeters. So it doesn't travel very far, and the main reason for that is primarily because it has a heavier mass, all right, compared to the beta particle, which is much lighter and will travel a distance of 200 to 300 centimeters. And then gamma radiation, which is even lighter because it's simply just a form of electromagnetic radiation, will travel much further, 500 meters. As such, alpha particles will travel a depth in biological materials to about 0.05 millimeters. Beta particles are more penetrative, 4 to 5 millimeters, and gamma rays are even more penetrative, will go as far as 50 centimeters or more in biological tissues. So that's the reason why these are the different types of shielding materials that are used to protect one from these particles. So in the case of alpha particles, they simply cannot pass through paper or clothing. Now, in the case of beta particles, you're going to need something heavier than just paper or normal clothing to protect yourself. So, as stated here, you're going to need heavy clothing, lab coats, and gloves. And then gamma rays, which is even more penetrative, you actually need something like lead to protect you from being exposed to gamma radiation. All right. And down here we have a list of the different sources of these different forms of radiation. Okay, so that's it for this first slide. So let me go to the second collection of slides, which deals with nuclear reactions. All right, and nuclear reactions are different from chemical reactions because in the case of nuclear reactions, what actually happens is that you have a change in the nucleus that is taking place, and the result will be basically the conversion of one element to the next. All right, so that's what we'll be looking at in this section. So there are different forms or different types of radiation, and in this particular case, we'll be looking at what is called alpha decay. Now, remember, the alpha particle is basically the helium-4 nucleus, which is shown here, right? So when you have a radioactive material like uranium-238, when it decays, it forms an alpha particle, and it also forms another particle, which is the thorium-234 nucleus, all right? So if you look at the changes that are taking place in terms of the atomic numbers and the mass numbers, you'll see that when the alpha particle is produced, the mass number, which was originally 92 here, becomes 90. So there's a change of 2 or decrease in the atomic number of 2 when the alpha particle is produced. And then if you look at the mass number, the change that it undergoes as you go from uranium 238 to uranium to, I'm sorry, thorium 234, is that the mass number changes by 4. There's a decrease by 4, right? Now, the reason for that is that basically, whenever you have any nuclear reaction taking place, two things must happen. The mass number must be conserved, and the atomic number must be conserved as you go from the reactant to the product, all right? And we can see that in this example right here, all right? So we're starting off with this particular nucleus. This is called californium, right? This is the atomic number, and this is the mass number, right? Now, when that emits an alpha particle, which has a mass number of 4 and atomic number of 2, you're going to end up with this particular nucleus, the name of which is, let me see if I can find the name here. CM is curium, all right? So curium is formed, and the atomic number is 96, and the mass number is 247. Now, if you look at the sum of the atomic numbers on both sides, you see that they match up, right? It's 98 here, and 96 plus 2 is 98. So the atomic number is conserved. Doesn't change totally as you go from left to right. And the same is true for the mass numbers, because the mass number of californium is 251, and the sum of the mass numbers of this curium and the helium for nucleus, the alpha particle, is also 251, all right? So basically, when it comes to balancing a nuclear equation, the sum of the mass numbers and the sum of the atomic numbers on both sides must be equal, all right? So that's something that you need to be aware of. And we can look at an example, which I think is coming up shortly. Well, no, not yet, but we're going to see how we can apply what we have just learned to balancing a nuclear reaction. Now, as stated here, when radiation occurs, in some cases, particles are emitted from the nucleus, and you may end up with a change in the mass number as well as the atomic number, depending on what particles are being lost. And we saw that in the previous example where both the mass number and the atomic number do change, all right? Now, here's where we're going to get into how do we write down a balanced nuclear equation. And these are the steps that we have to follow. The first step is that we write the incomplete equation based on the information provided in the question. The next step is that we determine the missing mass number, and then we determine the missing atomic number. And I'm going to show you how to do that. And then in step 4, we determine the symbol of the new nucleus. And the way we do that is that we look for the element in the periodic table that has the atomic number of the new nucleus, and then we can complete the nuclear equation based on that. All right, so that's basically how that is done. So here's an example. All right, so let's say you're given this question: write an equation for the alpha decay of radon 222. Right, so the first thing you'd write down here is the symbol for radon 222. Of course, you'd have to go to the periodic table, and when you go to the periodic table, you see that the atomic number is 86, and the question already gave you the mass number, which is 222, right? So this would be the symbol of radon 222. And it says that it produces an alpha particle because it says alpha decay. So on the right side, you would write down the formula for the alpha particle, which is the helium-4 nucleus represented here. So the question is, what is the particle that is produced along with the alpha particle? Well, because we know that both the mass numbers and the atomic numbers on both sides must be conserved, we can figure out what the atomic number of the question mark here and what the mass number is. All we have to do is subtract the 2 here from the 86, which is done here, and you're going to end up with 84. So we know that the atomic number is 84. And then as far as the mass number is concerned, we subtract 4 from the 222, which is done here, and the new mass number will be 218, right? So we know that for the element here, which we don't know what it is yet, we know that the mass number is 218 and the atomic number is 84. So how do we know what the element is? Well, we look for the element that has the atomic number 84 in the periodic table. And when you check it out, you see that the element that has the atomic number 84 is polonium, symbolized by PO, right? So now we can write down the balanced equation, and this is it right here, with the PO and the mass number indicated here and the atomic number indicated down here. And that's basically how we balance such an equation, all right? So that's a relatively simple exercise, all right? So the key thing you need to remember is that when balancing an equation, you have to ensure that the total number of, the total atomic number on both sides must be the same, and the total mass numbers on both sides of the equation must be the same, all right? Now let's look at what happens in the case of a beta particle being emitted from the nucleus. So when the beta particle is emitted, what actually happens in the nucleus is that a neutron is converted to a proton and an electron, right? As a result, this here, the electron is also the beta particle that would leave the nucleus, and you'll be left with the proton in the nucleus, all right? So an example of this would be the beta decay of carbon-14, right? So this is carbon-14, and when it loses a beta particle, it forms nitrogen-14, right? And you'll notice that the mass number does not change for the nitrogen going from carbon-14 to nitrogen-14, but the atomic number increases going from 6 to 7. And the reason why is because 7 minus 1 which is the total sum of the atomic numbers on the left side, is equal to 6, and that is basically the same as the 6 here for the atomic number of carbon on the right side, on the left side, I'm sorry. So basically, that's what happens in the case of an emission of a beta particle. There will be no change in the mass number, but the atomic number will increase by 1. All right? So here's an example. So let's say the question is, write an equation for the decay of potassium 42. All right? So we start off with the potassium 42, and then we know that the beta particle is emitted, so we write the formula for the beta particle here. So the question is, okay, so what's the formula for the nucleus that is formed here? So we know that the nucleus that is formed here, the mass number will not change, so we're going to put 42 here, but the atomic number will change because we have 19 here, we have -1 here, which means that the new atomic number here must be 20, right? So therefore, that's why we have the atomic number being 20. And then all we have to do from here is consult the periodic table to see which element has the atomic number 20, and that would be calcium, right? And therefore, as a result, the complete equation is what we have right here, where the new nucleus would have this formula here, and therefore this would be the final answer, all right? Okay, so that's what happens in the case of beta emission. So let's see if we can do this particular question here. So this question says, write a nuclear equation for the beta decay of cobalt 60. So what I'm going to do here is write down, write down the formula. Why did this happen? I'm going to write down the formula for cobalt 60. So cobalt, the mass number is 60, and then I would consult the periodic table, and according to the periodic table, the atomic number is 27, right? And we know that it emits a beta particle, so I'm going to write down the formula for the beta particle here. So the question is, what is the nucleus that is formed along with the beta particle? As I said before in the previous example, the atomic number will not change when a beta particle is lost, so I'm just going to put 60 here. But as far as the atomic number is concerned, this is 27, this is -1 on this side, which means that the atomic number here for the unknown nucleus must be 28, because 28 minus 1 gives you 27. So what I would do now is go to the periodic table and look up the element that has the atomic number 28, and that element will be nickel. So basically, I'm going to erase this here and put the symbol for nickel in its place, and that would be Ni, and that would be the balanced nuclear equation for the decay of cobalt 60. All right, so that's basically the answer for that question. Okay, in the case of positron emission, what actually happens is that a proton is converted to a neutron and an electron. And basically what happens is that there will be no change in the mass number, but the atomic number will decrease. And that is seen in this example right here. You're starting off with manganese 49, the atomic number is 25. When it produces a positron, basically the mass number doesn't change, but the atomic number decreases because 24 plus 1 will give you 25. And that corresponds to the element chromium, all right? So that's what happens in the case of positron emission. The atomic number decreases by 1, but the mass number does not change, all right? And gamma radiation, basically there's no change in the atomic number or mass number because the only thing that is lost is electromagnetic radiation, right, which has pretty much no mass nor no atomic number. So basically, this is what happens in the case of this element Tc, and I'll be honest with you, I don't know what Tc stands for. Let me do a quick check here. Tc is technetium, okay? Now, in order to make a distinction between this form of technetium and this form, where there's no change in the mass number, no change in the atomic number, we put a symbol M here. And basically what the M here indicates is that this is the unstable form of technetium. And then when it loses a gamma radiation, then it forms a more stable form, which is basically of the same composition, all right? Okay, so that's what happens in the case of gamma radiation. So this is basically a summary of the different forms of radiation that we looked at when these are emitted from a nucleus. In the case of the alpha emitter, it produces, of course, the alpha particle, and the new element that is formed would have a mass number that is less than 4 less than the original, and the atomic number would be 2 less than the original, right? In the case of something emitting a beta particle, the new element will have an atomic number which will be 1 greater than what it was before in the original nucleus. However, the mass number would be the same. In the case of positron emission, what happens is that in addition to the positron being emitted, the new element will have the same mass number, but this time the atomic number will be 1 less than what it was before. And then in the case of gamma emission, there'll be no change in the atomic number or the mass number of the element. So it's basically the same element, but a more stable form of the same element. All right? Okay. Another type of nuclear reaction that can occur is what is called transmutation. And what is basically happening in these reactions is that you have a stable nucleus, and then it is bombarded with some particle to form a new radioactive nucleus. And this is actually what is done in order to make radioactive nuclei for different purposes, right? For research purposes, for medicine. There's a whole area of medicine known as radiomedicine where they use radioactive substances to treat diseases and to do diagnostic testings and so on. So this is what is happening in this example that you're looking at right here. Basically, the boron 10 is bombarded with alpha particles, and then that creates a very unstable nucleus along with some other byproduct, a neutron in this case, right? And then this can be used for whatever purpose that is that it can be used for. All right. So that's basically what we mean by transmutation. You're transforming one nucleus, one element into another by bombarding it with some particle. All right. So let's look at this example. And basically, when it comes to balancing these equations, it's the same principle. The sum of the mass numbers must be equal to the sum. Wait, I'm sorry. The sum of the mass numbers on the left must be equal to the sum of the mass numbers on the right. And the same is true for the atomic numbers. So applying that concept, that principle, we can solve this problem right here. The question is asking what radioactive isotope, which is this right here, is produced when a neutron, which is this, bombards cobalt 59. All right. So basically, we look at the atomic numbers first. We see that the sum on the left side is 27, and we have 2 here, which means that the atomic number for this element must be 25. 25 plus 2 gives you 27. And then as far as the mass numbers are concerned, we have a total of 59 plus 60 on the left side. We have 4 here, right? The total on this side must be 60, which means that the mass number here must be 56. All right, 56 plus 4 gives you 60, which balances with the 59 plus 1. So, of course, we go to the periodic table and we look up which element has the atomic number of 25. And according to my periodic table, that element will be manganese, right? So the answer here is that the isotope that is produced is manganese 56. All right? So that is what is produced as a result of neutrons bombarding the cobalt 59 isotope. All right? So that's basically the answer to that question. Okay. That's it for this slide. So I'm going to start the video here. And the next, let me keep this here or discard that. And the next video will be dealing with radiation measurement. All right.